Hi, welcome back. Good evening. I hope you had a great day. Like I mentioned the last time, I'm going to bring to you today a book review. It's been a very long time since I talked about books at Girizada, and there are loads of books to, be talking about, including some very interesting books that have come out recently, like The Nutmeg's Curse by Amitabh Ghosh, and I hope to review that book sometime soon. But for today, I'm going to be taking up a book which I hope I will do justice to, and I'm really not sure if I'm going to be taking a lot more than I can chew at this point of time. But I thought it's worth the effort because I'm going to be talking about a topic which is very close to my heart and which I believe is very important from the point of view of education. And the book that I'm going to talk about has a quite central role in that challenge. So let me begin by talking about the way we teach children mathematics. The moment you talk about mathematics, uh, there are some really extreme reactions that come from parents, children, of course, and teachers. And all of these extreme and sometimes negative reactions, uh, have a word, and that is called as math phobia. Math phobia, can arise because of various reasons, but one of the most important reasons is, of course, a lack of understanding, a clear, uh, uh, cut confusion about the subject. You don't understand what the teacher is saying. You don't understand the ideas, the concepts that are taught, and so on. So pretty soon you begin to hate the subject because, unlike other subjects, maths has its own language and there is logic built into it, and you need to approach the subject in a particular uh, manner. But what happens mostly in schools across our country is that maths is presented as a subject which has the right or wrong answers. There's nothing else. It's a very, very narrow and unidimensional way of presenting the subject. It's almost a burden, that you have to get the right answer. And if you manage to do that in the exams, of course, it's great for you. But then if you don't, then, God help you. So pretty soon, over a period of time, a large number of students begin to dislike the subject. They begin to hate it, and in most cases, it leads to what I, characterized as math phobia. When I go back to my own math learning in school, I'm talking about high school specifically. We had a fantastic teacher in Bangalore, involved in Boys High School at that time, called Chanakeshwar. And I've had the privilege of being taught by this great mathematics teacher, very inspiring teacher and personality. And of course, I had the honor and privilege of writing a book about him. More about that book, perhaps in another episode at Girizada. So, what did Mr. Chanakeshwar do? He presented mathematics as a story. The stuff that we were doing in the textbooks, the problems that we were trying to solve, he placed them in a context. He told us why these different branches of mathematics came up, what were the reasons for their uh, development, who developed these particular areas of mathematics like geometry, algebra, trigonometry, and so on and so forth. And he also looked at specific topics within those uh, areas that we studied to tell us stories about how they were developed. And invariably, these stories are human stories. These are stories of people who have struggled to find patterns, to find uh, underlying meaning, to find unity, and so on. So mathematical knowledge is all about pattern finding, understanding deeper meanings, and so on and so forth. So I think one of the reasons why Mr. Chanakeshwar's teaching remained with me for so long, and I wrote a book on him almost 3 decades after I graduated from school, is because of these stories. He humanized mathematics, and I think that is one of the things that we must try and do. We must, bring in a lot of history into the teaching of mathematics, and it's a very powerful tool to illustrate how mathematics as a discipline and as a subject hasn't just come from above for us to catch, but then it is very much part of the intellectual journey of human beings of various civilizations across the world. What does all of that have to do with this book review? You'll get to know very soon. So as I said, the point that I made was that we unfortunately present mathematics as a set of formulae, as a set of theorems and truths that either are false or true, or when we do problems from the exercises, we say this is the right answer and you have to get there, and the wrong answer, and so on. So it's a very, very sterile way of teaching mathematics. I have a book with me, which I'll let me first show you this book. Have a good look at it. The Great Problems of Mathematics by this gentleman called Ian Stewart, who happens to be an emeritus professor of mathematics at Warwick University in the United Kingdom. And of course, he is the fellow of the Royal Society. Now, Ian Stewart is a very, very well known math popularizer. He has written a lot of books. And this is one of the books that I have laid my hands on this evening. It talks about the great mathematical problems. And why have I chosen this book? I think I see a lot of value in a book like this for the teaching of mathematics, both at the school and college, tertiary levels. And I've already made my case that it is presented in a very dry, sterile kind of manner. What does Ian Stewart do here which excites the imagination and which gives us hope that we can look at the teaching of mathematics differently? Mind you, this is not a book on how to teach mathematics better, but then as somebody who's working in the field of education, I see a lot of value there. So what Stewart has done is he has defined a category of mathematical problems as the great mathematical problems. And of course, what makes a mathematical problem, a great one? I'll just read out from his book. He says, what makes a great mathematical problem great? And Stewart says, intellectual depth combined with simplicity and elegance. Plus, it has to be hard. It has to be like climbing Mount Everest and not climbing a hillock in your neighborhood. And a great problem is usually simple to state. This is his definition of what a great problem should be. It's something that everyone should more or less be able to understand. It should be stated simply, but of course it should be hard. Many of the problems that Stewart has described in this book are problems that took hundreds of years for mathematicians to solve. There are many problems. He has, of course, listed 14 problems in this book, 14 great mathematical problems, and he's left 12 for the future generations of mathematicians who can solve them and add to the ever-growing knowledge of the discipline of mathematics. Why are we discussing mathematical problems, and especially these problems that are called as the great mathematical problems? One is that if you solve a problem that has resisted solution for a long time, you're then trying to find various ways of arriving at an answer. And in the process of doing that, you're also discovering many things along the way. Uh, if this story can be told to children in terms of its key characters, in terms of the plots and twists, that occur along the way, then suddenly maths can come alive, as it did for me when I was a student and when Chanakeshwar was my teacher. Let me give you a very simple illustration of where he got as excited about mathematics through these stories. In fact, in his teaching, I think we learned about three or four great mathematical problems at that time. I'm talking about the early to mid 80s when I was in high school, having graduated in 1985. So one of the problems at that time which was unsolved was a famous problem called as Fermat's last theorem. So very simple to state. For those of you who know, Pythagoras's theorem, it says that the square of the hypotenuse on a right angle triangle is equal to the sum of the squares on the other two sides of that right angle triangle. So typically, if you have the other two sides, one side 3 centimeters, the other side 4 centimeters, then this hypotenuse will be 5, because 3 square plus 4 square equals 5 square. And there are many such examples. You can cook up these numbers which are called as Pythagorean triples. You can have millions of such sets of Pythagorean triples actually. Now the problem becomes very interesting when you ask this question. Okay, this equation seems to be holding good for a square plus b square equals c square. What about a cube plus b cube plus c cube? So are there three numbers whose cubes are related to each other in such a way that the sum of two cubes, for example, it can be x cube plus y cube equals z cube. So the question is, what is x, what is y, and what is z? And does such an equation even exist, right? If it holds good for squares, does it hold good for cubes? Does it hold good for fourth powers, fifth powers, and so on and so forth? Now, this problem was solved only after 350 years of effort, and it was solved by a mathematician called Andrew Wiles in 1993. And certainly when I was studying in 85, when I graduated out of 10th standard, the problem was still unsolved. But at that time, Andrew Wiles was beginning to attack the problem with all the tools that were available to him as a mathematician. All the tools that anyone had developed in the world at that point of time to crack this very simple sounding problem fascinated me. I mean, why solve these mathematical problems? I think I would go to the extent of saying that if mathematics had not had problems like these and not had questions like these, the subject would not have advanced at all. And we wouldn't have had these fascinating stories, that talked about how difficult the lives of mathematicians have been in their attempts to, uncover more mathematical truths, uncover more beauty and elegance in that particular subject. So this story that Chanakeshwar told us about how this problem has been an impossible problem to solve at that point of time was revelatory. It was, it completely turned my understanding of mathematics on its head, because around that time we were still, somewhere, at the subconscious level, you think that, oh God, this is such a boring, sterile subject. We have to just solve some problems, get it right, and get all the marks in the exams and so on. And suddenly here comes a teacher who says, hey, look, mathematics is not just about solving problems to get the right and wrong answers. There is a story to it. There is a story behind everything that you study in your textbooks. And let me tell some of those fascinating stories for you. So this book, of course, as I said, Stewart has his own set of 14 great mathematical problems. And very quickly over the next few minutes, I will give you a glimpse of one or two of those problems. I've already talked about Fermat's problem. It's solved, of course. But that still doesn't take away from the fact that it's a great mathematical problem, because it took 350 years and it led mathematicians across the world on a wild goose chase. It resulted, in fact, in newer areas of mathematics that had to be invented because uh, Andrew Wiles and a whole range of other mathematicians who have contributed to the solution to this problem, to the solution of this problem, just didn't have those mathematical tools. They had to develop them over time. What are the other problems that Stewart discusses? And one of my favorites is this problem called as the Riemann hypothesis. Again, of course, Riemann is the German mathematician. You can check him out on the web. Fascinating stories about him. Most notoriously connected with this hypothesis called as the Riemann hypothesis. What is it about? It's about prime numbers. Okay, all of us have studied prime numbers. For example, a number such as 3, a number such as 5. 8 is not a prime number because it can be factorized. For example, 8 is 4 into 2, and so on and so forth. So a prime number is a number which cannot be broken into smaller factors. So for example, 7, you can only look at 7 as 7 into 1 or 1 into 7, whereas 8 and a prime number is a number that cannot be further broken down. For example, 13, whereas 8 can be broken down as 4 into 2, or 12 can be broken down as 2 into 2, that is 4 into 3. So in terms of the prime factors, that's the difference between 12 and 7, for example, right? So now all these numbers, these prime numbers on the number line, we have all studied the number 9 basically. And then if you ask the question, what is the formula for finding out the next prime number? Is there a pattern? Is there a particular way in which these prime numbers, which are actually building blocks of the number world, much like your atoms or your electrons are building blocks of matter, which we also study in physics and chemistry and so on. So the question is a very simple and very, very simple but deceptive question. So we have the first few prime numbers. I can rattle them off for you. 2, 3, 1 is not a prime number. I'm not going to get into why 1 is not a prime number. We leave that for now. 2, 3, 5, 7. Is 9 a prime number? It is not, because 3 into 3 is 9. 11, 13. Is 15 a prime number? No. 17, 19, and that's how it goes. The fact that prime numbers are infinite, there's no end, has already been established, and that was established more than 2000 years ago by Euclid, the great Greek geometer, in a very elegant proof. But then the question of how are they distributed, right? When is my next prime number going to come? Is there a formula where I can plug in some numbers and discover whether that number is prime or not? And you'll be surprised to hear, and this is a problem that's already more than 150 years old, probably 160 years old as I speak. The answer is that there is simply no formula or understanding about how the prime numbers are actually distributed. So much so that one of the great mathematicians of the modern era, David Hilbert, who spoke in 1900 at the International Congress of Mathematics in Paris, made this statement. I think he, in fact, at that point of time, he had listed about 23 problems of mathematics which he thought were fundamental and which he wanted mathematicians to solve, so that the subject could be advanced, right? And the story goes that on the Riemann hypothesis, which is of course part of his list, he hoped that there would be a solution, but then he also felt that this problem would resist that solution. So somewhere the gut feeling that he had as a mathematician was that this problem is going to be tough. It's not going to easily, be resolved. And he's supposed to have said that if I wake up after 500 years after a deep slumber, the first question that I'm going to ask is the Riemann hypothesis solved? In other words, simplifying it, have we found a formula that can predict where the next prime number lies or not, right? So see how beautiful and simple and elegant this problem is. But then if it has eluded solution for 150, 160 years, then there is something, in it. So Ian Stewart's book is a collection of such notoriously difficult problems in mathematics that have resisted solution. Why are they important from a strictly mathematician's point of view, or from a strict point of view of the subject itself? The subject doesn't advance unless you keep attacking new problems. Very much like science, there are so many solutions that you've found to patterns in the natural world, but then there are many other patterns that have resisted understanding, right? So similarly, it's with mathematics. It's a very this is how it grows. The subject keeps growing, and as it keeps growing, it keeps accumulating new truths, new relationships, new patterns, understanding of these patterns, and so on. So the second point is, of course, what does it mean? I mean, why am I fussing over this book from the point of view of education? What does it have to tell the child? So as I said, a discussion on the great mathematical problems in the classroom. And mind you, many of these problems can actually be discussed in a classroom, in a high school classroom, where you can simplify it. And there is quite a lot of material available on the web now. Of course, this is one book. There are many other books. We can talk about them sometime, which will help a teacher to simplify, the mathematics there, and more importantly, convey the excitement of that particular story, to get children excited about it, to get children imagine things. And let us not forget that Andrew Wiles, who ultimately cracked the 350-year problem of Fermat, actually encountered this theorem, or this problem, the Fermat's last theorem as it is called, in a school library when he was just 10 years old. And he was going through some, books in his library, and he came across this problem, and it really excited his curiosity. And a great mathematician was born just by that intersection, that through that interface with a piece of literature in the library. So imagine what teachers can then do. The idea is not to make everybody a mathematician, of course. That would be such a boring thing to do. We need all kinds of people. But then get children to discard notions of mathematics as something that is boring, dull, sterile, meaningless. It's just meant to be for the examinations, and let's be done with it. Let's get our marks and be done with it. So like any other intellectual adventure, the mathematical adventure is as rich, as gripping, with as many plots and twists and turns, including all the politics and emotions that you can think of. And the more we read about all of this, the more we actually get a glimpse of human nature itself. So I hope that this very brief introduction, I'm already 24 minutes into this, is something that will excite you to purchase your copy of this book. Also do check out other books that Ian Stewart has written. And lastly, before I sign off from this review, I want to quote Stewart from this book. He says, almost in defense of why he has written this book and what it can perhaps matter mean for education, though it's strictly not a book meant for the teacher. It's not a book that the teacher can directly use, but then can be inspired by to, do something in the classroom. So Stewart says, all too often, School mathematics is presented as a closed book in which every question has an answer. Students can easily come to imagine that new mathematics is as rare as hen's teeth. So, can we really change the way mathematics is taught so that students get a much better handle on it, and more importantly enjoy those journeys that have been undertaken over several thousand years to arrive at where we are today? And a book like this and a discussion on some of the greatest intellectual challenges of the subject of mathematics. And remember, there is no final word on many of these problems. So mathematics suddenly looks very vulnerable. It's no longer that cold, austere science, that pure, so-called pure science that has all the answers and all the formulae. So it's mathematics is anything but that. It's a very incomplete and unfinished science full of curiosities and excitement along the way. So take care then. I hope you like this. Do let me know what you thought about this review, and look forward to meeting you again soon. Bye bye.